In this video, we're going to look at the resultant force in 3D, and we're going to also calculate the magnitude of the resultant as well as the angle that the resultant will make with the z-axis. So say we have two forces that act on a point in space, somewhere in space, and one of those forces happen to be F1, which has a magnitude of say 120 newtons. Now let's say F1 acts from point A to point B, and the coordinate that we have for point A is say 2, -1, and 3. Now these are for the X, Y, and Z axes respectively. And let's say our force acts from point A to point B, located at 6, 3, and let's say 9. Now we have more than one forces, so we're going to introduce another force here, F2, and say we're given the vector components for F2 as 40i, and let's use 20j and plus 80k. Now because this is a force, it's newtons that we'll use for the unit. Now we're going to evaluate the magnitude of the resultant first, but there are a few things that we need to do before we get to that point. So let's look at them in step-by-step analysis. So the first thing that we need to do here is to find the direction from A to B. So we're looking at the direction from A to B. So how we write that in terms of its vector form is AB, vector AB equals OB minus OA, and these are all vectors. And in terms of the logic of that, I'll just sketch a side note here for you to see what's happening in case you don't get this bit. So let's say we have this coordinate grid, and out here in space, somewhere in space, we have the vector that we're talking about, vector AB. Now, how we would typically draw this out is we would have OA, vector moving from the origin, so that's O to A, and then O to B to close that shape there. So we get a triangular forces there. Now what happens is we are going to first of all add the vectors that are going along the same path. So that would be OA plus AB, and because our OB would now be going opposite to that, then all of this would be equal to OB, which goes in the opposite direction. I hope that makes sense. So this is what we would end up with. We follow the arrows, so we're going from O to A and plus A to B, and because the next vector, which is OB, would be going in the opposite direction, we would have that as BO, and we don't want that, so we put these equal to OB. And then if we rearrange this now, we would end up getting that AB is equal to OB and minus OA. So that's where that comes from, just for clarity. So let's work out now what we should have then for our vector AB, because we're just going to subtract OB and OA. So AB is equal to, so we're just going to subtract the components here of A and B. So let's look first at the X component. So that's 6 and take 2. So the X coordinate in B, OB, is 6, and the X coordinate in A is 2. So we're going to do 6 take 2, and that's the I component. Plus we do the same thing now. We're going to do 3, so that's our 3 right there, and take that -1. So we have 3 take -1. And that right there is our J component. And plus, to get our K component, we're just going to have 9 and take 3. and this is our k component. So we have then that vector AB is equal to 6 take 2, so we have 4i and plus 4j plus 6k. So this here as a vector for AB, it gives the direction only and not the force yet, which is where we're going next. So I'm going to just clear this and we analyze what we do next in order to get the magnitude of AB. So we get our vector AB as 4i plus 4j plus 6k, and we already established that this gives the direction only and not the force yet. So to find the magnitude of AB now we need a unit vector, and a unit vector has a length of 1. So we can apply the force magnitude here properly now. So how we do this now to find the magnitude of AB? What we do here is the square root of, and we're going to take the coefficients of I, j, and k, square them, and add together. So we have 4 squared for the x part, 4 squared again for the y part, and 6 squared for the z part. And this gives us a total of 8.2. I'll just write it to 3 decimal places. So that gives us a magnitude of 8.246. Now, once again, this magnitude is not the force yet. It is only the length of the direction vector. So we need it now so we can turn the direction vector into a unit vector. So that's what we're going to do now. We're going to form the unit vector. Now we know that a unit vector, as I've said before, it has a magnitude of 1. So we need to then divide each component by what we have here that we got for the magnitude. So I'm just writing this notation that says our unit vector AB should be equal to, so we're going to divide the 4 right there. So we have 4 divided by 8.246i plus same thing 4 divided by 8.246j and plus 6 divided by 8.246k. And our unit vector for AB is now 0.485i and plus again 0.485j because it's the same quantities we have dividing, and plus 0.728k. Now once again, the unit vector here, it gives direction only. It's not yet a force magnitude, which is what we're going to do next. We're going to express this now in its force form I, j, and k. So for this, we're going to have that the force is equal to our magnitude and multiply that by our unit vector. Now we already know that the magnitude which was given in the question, we established that the magnitude was 120. So we're going to multiply then 120 as a scalar quantity by our unit vector AB. So what that will give us then is F1 equals 120, and this will be multiplied by what we got up top right here. So that will be multiplied by 0.485i and plus again 0.485j plus 0.728k. So we're going to just expand this as a bracket pretty much. So F1 turns out as 58.2i, another 58.2j, and 87.2 0.4K. And this is a force, so our unit is Newton here. Now, a common mistake is to use the direction vector directly instead of the unit vector. So we have to make sure that we safeguard against that. So now we're going to find the resultant force vector. And this is typical calculation for resultant. So R for resultant is just going to be F1 vector plus F2 vector. And we have both of these given already. So R will then be equal to what we have for F1 up top. And initially I wrote down F2 as 40I, take 20J plus 80K. So this was our F2. So let's put them together now so we can evaluate what our resultant vector is. So for F1, it's exactly what we have up top. So that's 58.2I plus 58.2J and plus again 87.4K. And we're going to add to that now F2, which is 40I take 20J and plus 80K. So of course what we add together, we will add our X components, our Y components, and our Z components. So these are what we're going to add together to get our resultant vector. So what we get here then is R, our resultant vector, as approximately 9.98 here, 0.2, so 58.2 plus 40I, so 98.2I, plus here, this will be 38.2J, and plus this will be 167.4K. And this is in Newton. So this here represents our resultant vector. Now the resultant force is just the overall combined effect of both forces. So we just simply added the X components together, the Y components together, and the Z components. One important thing is just never add the magnitudes directly unless the force itself acts in exactly the same direction. So now we can find the magnitude of this resultant force that we have here. So let's do that. So the magnitude then of the resultant force is exactly as we did before when we found the magnitude of AB. So this now is going to be 98.2 squared, same as what we have up top there, plus our 38.2 squared, and plus 167.4 squared. And we just need to put that into the calculator. And this gives us a magnitude of our resultant as 197.8 here. So that's our magnitude. And now the magnitude itself, it tells us the overall size of the resultant force after combining all three directional components. Now the last thing we're going to do here is to find the angle that the resultant will make with the z-axis, as you're typically required to find the angle, the direction, the angle, the magnitude of the resultant, that sort of thing. So to find the angle with the z-axis, we need to compare the component to the total magnitude. And this will simply be cos theta equals the z component of the resultant over the magnitude of the resultant. Now RZ is right here, which is our 167.4. So we're going to have then cos theta equals our 167.4 divided by our 197.8 that we got for the magnitude. So therefore we take cos inverse of that. So if we do for the angle now, rearrange to get the angle, we're going to have cos inverse of, when we divide what's there, the 167.4 divided by the 197.8, we get that. So cos inverse of 167.4 divided by 197.8, and this gives us an angle of 32.2 degrees in relation to the z-axis. And if you wanted to find another axis, it would just be the same thing. So you just, let's say we wanted to find the angle in relation to the y-axis, we just do cos inverse of 38.2 and divide by 197.8. Now if you want more problems like this, especially on 3D vectors and even 2D vectors, then please check out this next video right here.